Section: Introduction. In this section, we will discuss the rise in popularity of large language models, LLMs, leading to various model-as-a-service options and open-source developments. It has become crucial to compare these frameworks systematically to ensure a good user experience and cost-effective deployment. The current evaluation metrics like time to first token, TTFT, time between tokens, TBT, normalized latency, and time per output token, TPOT, do not fully capture the user experience in real-time LLM interactions. We argue that these metrics are valuable but insufficient for dynamic LLM inference. We propose a more detailed approach considering the timing of token generation and its impact on user satisfaction. While metrics like TTFT and TBT capture latency for individual tokens, they do not represent the overall token generation throughput. On the other hand, normalized metrics such as TPOT and normalized latency try to measure token throughput but do not identify specific user experience issues like inter-token jitter or scheduling delays. This gap emphasizes the need for a comprehensive evaluation framework that summarizes the overall user experience. To address these limitations, we introduce Metron, a framework with two new metrics, fluidity-index and fluid token generation rate. These metrics aim to capture the nuances of real-time LLM interactions. The fluidity-index metric is inspired by evaluating periodic tasks in real-time systems and focuses on maintaining a smooth token generation rate. It sets token-level deadlines to measure how many deadlines are met within a request, reflecting the system's ability to generate tokens consistently. On the other hand, the fluid token generation rate determines the maximum sustainable playback rate while maintaining fluidity. By using Metron, we evaluate both open-source and proprietary LLM inference systems to understand their strengths and weaknesses. This framework provides a detailed view of LLM performance aligned with real-world user experience. We have made Metron open source to set a standard for user-centric performance evaluation in the evolving landscape of LLM systems and frameworks. Moving on to the background, we will describe the typical LLM inference process, common performance metrics, and an overview of open-source and proprietary inference solutions. In the LLM inference process, there are two main phases, prefill and decode. The prefill phase processes the user's input prompt to generate the first output token, while the decode phase generates subsequent tokens one at a time until an end-of-sequence token is reached. The decode phase also requires access to key and value pairs associated with previously processed tokens. The conventional performance metrics for LLM inference include time to first token, TTFT, time between tokens, TBT, time per output token, TPOT, normalized latency, and capacity. TTFT measures the latency from request arrival to the first output token, TBT measures the latency between subsequent token generations, and TPOT calculates the average time to generate an output token. Normalized latency considers the total execution time normalized by the number of decode tokens, while capacity indicates the maximum request load a system can handle while meeting latency targets. These metrics help assess the efficiency and responsiveness of LLM systems. Section Summary. In this section, we delve into the importance of evaluating user-facing performance in large language models, LLMs, inference systems. Current metrics like TTFT, TBT, TPOT, and normalized latency fall short in capturing the dynamic nature of real-time LLM interactions. To address this, we introduce Metron, a framework with novel metrics like fluidity-index and fluid token generation rate, aiming to provide a more comprehensive evaluation of LLM inference systems for a smoother user experience. These metrics consider token generation variability and playback rate to align performance evaluation more closely with real-world user satisfaction. Section: LLM Inference Framework Evaluation. In this section, we will discuss how we evaluate the user-facing performance of LLM serving frameworks, both in open-source and proprietary model offerings. When it comes to open-source frameworks like VLLM, Sarathi-Serve, Light LLM, and text generation inference, assessing their performance can be tricky due to the many adjustable settings they have. It's crucial to accurately evaluate their performance during deployment to figure out the maximum workload a cluster can handle while still meeting specific speed targets. On the other hand, companies like OpenAI, Azure AI Studio, Fireworks AI, and Grok offer model-as-a-service solutions that usually limit how much users can tweak the system's performance. This means users and developers can only passively evaluate performance based on their specific tasks. Comparing performance across different services mainly relies on observable factors like speed and cost. This emphasizes the need for methods that can help users choose the most efficient and cost-effective service for their particular needs. When it comes to evaluating LLM inference systems, traditional metrics like latency and throughput are not always enough to give a complete picture of the user experience. For example, metrics like time to first token, TTFT, may not consider the length of the prompt, leading to incomplete assessments. Normalized latency can hide details like scheduling delays, while metrics like time per output token, TPOT, may not reveal intermittent stalls during token generation. To address these limitations, we introduce a new metric called Fluid Token Generation Rate, which focuses on the actual rate at which tokens are generated while ensuring a good user experience. This metric considers factors like meeting token generation deadlines with a certain level of fluidity. By using this metric, we can better understand how well a system performs under quality of service constraints and user expectations. Section Summary. In this section, we evaluate the user-facing performance of LLM serving frameworks, both open source like VLLM, Sarathi-Serve, and proprietary offerings from companies like OpenAI and Azure AI Studio. While conventional metrics like time to first token, TTFT, and normalized latency are useful, they may overlook important aspects like scheduling delays and token generation jitters, leading us to propose a new metric called Fluid Token Generation Rate to better assess system throughput and user experience. Section: Desirable Properties of Evaluation Framework. In this section, we discuss the desirable properties of an evaluation framework for LLM serving systems. We have recognized the limitations of current metrics in assessing these frameworks and have outlined the key characteristics of an ideal evaluation metric. Firstly, we aim for an evaluation framework that can assess any API endpoint without being influenced by the workload's variations, such as differences in prompt lengths. Secondly, due to the complexity of interpreting system performance from multiple metrics, we emphasize the need for a unified metric that simplifies analysis and accurately represents the user-facing performance of LLM serving systems while considering the unique aspects of the inference process. Lastly, the metric should encompass the frequency, duration, and timing of stalls within the system, which significantly impact user experience. Let's consider the design and implementation of Metron. Suppose we have the ideal time to first token, TTFT, and time between tokens, TBT, for an application based on expected user behavior. The current TBT-based metrics may not effectively capture user experience as they treat each token generation independently. For instance, if a system generates 10 tokens at 10 milliseconds intervals and the 11th token at 150 milliseconds, it is perceived the same as a system producing 10 tokens at 100 milliseconds intervals and the 11th token at 150 milliseconds. However, the first system is superior despite the same TBT miss rate. To address this, we suggest introducing a deadline for each token's generation to better reflect user experience. In our proposed approach, we define a deadline for generating each token based on the desired TTFT and TBT. As long as all tokens are generated within their deadlines, users will not experience delays or stalls, even if some tokens are generated with delays exceeding the TBT. We introduce the concept of deadline miss when a token's actual generation time surpasses its deadline. To prevent cascading effects of deadline misses, we reset deadlines after a miss and calculate subsequent deadline misses accordingly. This method ensures a more accurate assessment of system performance. The fluidity-index metric quantifies the percentage of accepted deadlines based on the defined criteria. It sets deadlines for future tokens considering prefill and decode latency targets, with a scheduling slack to accommodate variations. If a token is generated early, the slack is added to future token generation, while missed deadlines trigger a reset of all future deadlines. Setting practical latency targets, such as the prefill and decode latency, is crucial for the metric's accuracy. Prefill latency targets should be tailored to the input prompt length, while decode latency targets can vary based on the application's requirements, such as interactive or low-priority applications. These targets should be determined empirically to ensure effective evaluation of LLM serving systems. Section Summary. In this section, we outline the key characteristics of an ideal evaluation metric for language model, LLM, serving frameworks. We emphasize the importance of a unified metric that simplifies analysis and accurately reflects user-facing performance, while considering the unique dynamics of the inference process. Additionally, we introduce the concept of a deadline-based token generation time, TBT, acceptance rate metric, termed fluidity-index, which ensures that all tokens are generated within their deadlines to prevent user-perceived delays or stalls. Section: Evaluation Workflow and Implementation. In this section, we present the evaluation workflow and implementation of Metron. Metron offers a standardized evaluation process for both proprietary and open-source LLM inference frameworks. We provide two evaluation recipes: black box evaluation and capacity evaluation. In black box evaluation, we assess an LLM inference API endpoint by sending various requests with different prompt lengths to the server. We track the generation timestamps of each output token to calculate metrics like TTFT, TBT, and TPOT. By setting a target fluidity index threshold, Metron determines the minimum TBT deadline needed to meet this requirement, ensuring a smooth token throughput for users. Capacity evaluation helps operators determine the minimum number of GPUs required to serve users with specific quality standards when deploying an LLM inference service. Metron's capacity evaluation module assesses the system under different request loads to identify the maximum capacity each replica can offer while meeting fluidity index slow requirements. For implementation, we modify an open-source tool, LLM Perf, to support multiple LLM APIs, particularly those compatible with OpenAI APIs. We enhance the codebase to work with the open-source LLM inference framework VLLM, calculating various metrics and conducting capacity searches. In the evaluation section, we showcase Metron's effectiveness in evaluating the performance of various LLM inference systems, including both open-source frameworks and proprietary solutions. We demonstrate how Metron can benchmark public API endpoints by conducting black box analyses to understand their performance under different configurations. When evaluating public APIs, we analyze three proprietary systems, Anyscale, Grok, and Fireworks, using two models, Llama 3-70B and Mixtral 8x7B. By running Metron hourly for 24 hours to accommodate varying traffic patterns, we observe throughput using metrics like TPOT, tail TBT, and fluidity index. These metrics reveal insights into the system's performance, such as Grok's high TPOT throughput but lower tail TBT efficiency due to potential stalls. Furthermore, we evaluate open-source systems like VLLM and Sarathi serve on Llama 3-8B to assist deployment operators in setting SLOs and capacity planning. By comparing these systems under different metrics like TPOT, tail TBT, and fluidity index, we can determine their true throughput capabilities and efficiency in meeting service-level objectives. Section Summary. In this section, we present our evaluation workflow and implementation details for Metron, a tool that standardizes the evaluation process for both proprietary and open-source large language model, LLM, inference frameworks. Metron offers two evaluation recipes: black box evaluation, which assesses LLM inference API endpoints by analyzing metrics like TTFT, TBT, and TPOT to determine stable token throughput, and capacity evaluation, which helps operators determine the minimum GPU requirements to meet service quality needs. We demonstrate Metron's effectiveness in evaluating various LLM systems, including public APIs like Anyscale, Grok, and Fireworks, showcasing throughput differences based on metrics like TPOT, tail TBT, and fluidity-index to assess system performance and user experience. Section: Discussion. In this section, we present an evaluation framework called Metron for Large Language Model (LLM) Inference. We use a metric called fluidity-index to measure missed deadlines per request. Our main focus is on discussing the challenges that we plan to address in future research. The fluidity-index metric requires us to set a deadline for each token in the inference process. For the first token of each request, this deadline is the target latency for the prefill phase. We propose a method for selecting this prefill latency target by analyzing the prefill processing curve for different prompt sizes. However, determining a deadline for a specific prompt length is difficult for proprietary systems because we may not have a precise understanding of their prefill performance. Scheduling delays can affect the observed prefill time, making it challenging to predict prefill processing accurately. We aim to explore alternative approaches for setting prefill latency targets in future studies. Additionally, we recognize the need to introduce a small scheduling slack in our deadline calculations, as discussed in a previous section. We determine this slack value based on our practical observations and plan to further investigate how to systematically define this slack in future work. Furthermore, we acknowledge that open-source systems offer various performance tuning options, such as adjusting chunk size in Sarathi Serve and block size in VLLM. Currently, Metron does not automatically optimize these parameters but expects users to configure them during evaluations across different systems. In the realm of related work, machine learning inference systems have been extensively researched in the past decade. Various strategies, including caching, placement, and batching techniques, have been proposed in systems like TensorFlow serving, Clipper, Batchmaker, and Clockwork to enhance model serving efficiency. Recent works like Orca, VLLM, and Sarathi focus on addressing specific challenges in autoregressive transformer inference through efficient memory management and scheduling. Other approaches, such as splitwise, distserve, and tetri-infer, have introduced methods to separate the prefill and decode phases to avoid interference between them.